Hello everybody. Today we'll be discussing about electric flux. We would learn how to calculate electric flux through a given plane surface. So let's begin with that. Flux through a plane surface in a uniform electric field. Now here we are having a surface. This is a plane circular surface through which we have to find out the flux. Let's see how to proceed for calculation of flux. The first step would be to draw a normal perpendicular to this surface. So we could draw this draw the normal to this surface over here. So let's draw the normal. This is the normal perpendicular to the surface. Next, we would find the field at this point on the surface of sphere. We would note its direction and its magnitude. So the field at this point, let's draw the direction of field at this point on the surface of Suppose at this point on the surface, this direction shows the direction of field. This is the normal to the surface. Next, we would mark the angle. We would note the angle between these two, between the normal to the surface and electric field. This theta is the angle between the normal to the surface and the electric field at a point on the surface. Now the formula for flux. It's simply the product of three quantities: the electric field strength E, area of the surface S, and cos theta. This is the formula. Electric field strength E, area S, cos theta. ES, cos theta. Now if we know the formula for this flux, we can find out its unit by multiplying the unit of electric field and the unit of area. Cos theta does not have any unit. The unit for electric field is Newton per coulomb. That of area is meter square. Multiply the two. So the unit of flux is Newton per coulomb into meter square, or Newton meter square per coulomb. So this is the basic way how to calculate the flux through any given surface. Next, let us see a few examples of calculating flux. Some special cases. Consider this special case where we have a plain rectangular surface and this is the direction of electric field lines. The electric field lines are running parallel to the surface and we are supposed to find the flux through it. We would first draw the normal to this surface, as in the previous example we did. So first draw the normal to the surface. This is the normal to the surface. Now we can note that normal to the surface and the electric field, in this case, they are perpendicular to each other. So theta is 90. Now we'll use the formula for flux. Phi is ES cos theta. Cos 90 gives you 0. This is the first thing which we marked. Electric field is perpendicular to the normal to the surface, theta 90. So the flux phi ES cos 90, that becomes 0. So whenever this is the case, when the field lines are running parallel to the surface, we get flux as 0. Let's see some other examples where we'll have the same thing. Just see this surface. Here also the field lines are running parallel to the surface. So here even the normal to the surface and field are perpendicular. Another example, this one. This is a plane surface having its normal in this direction, rightward direction, electric field pointing in the upward direction. Here even the electric field and normal are perpendicular to each other. So even in this case, flux is 0. So in all these cases, we can see that electric field and normal are perpendicular. theta 90, and hence the flux is 0. There is yet another example, another special case. That is this case, where this is a surface and the lines of forces, they are crossing the surface perpendicularly. Let's compute the flux in this particular case. We'll begin the same way by drawing first normal to the surface. This is the normal to the surface which we have drawn. Now see that the normal to the surface and electric field, they are in the same direction. Theta is 0. Electric field and normal are in the same direction, parallel. Theta is 0. So flux is Es cos 0. Cos 0 is 1. So the flux comes as E into S. Write it down. This is the thing. Flux is E into S. So in such cases, when the field lines are crossing the surface perpendicular, flux is maximum and its value is Es. Let's see a few other diagrams where we'll find the flux to be maximum. This one. It's also the same case. The difference is only that the surface is having a circular boundary. Or this case, here even, it's the same thing. Direction of field is changed. Orientation of the surface is also changed. But still, these two are in the same direction. Electric field and normal. So this was the basic of flux. Next we'll discuss flux as a dot product of two vectors. So this was the basic diagram which we started with. A surface was given to us. We have marked normal to the surface, electric field, angle between the two. Now this normal to the surface, along this direction we'll mark a unit vector. We'll call it n cap. So I'll replace this by a vector. So n cap is in this direction. This n cap has magnitude 1. It's a unit vector. This is the direction of electric field. Its strength is E. Now let us compute a quantity which is the dot product of these two, which is dot product of this electric field vector and n cap. E dot n cap is mod E mod n cap cos theta. Mod E is the strength of electric field E. N cap, as it's a unit vector, its magnitude is 1 cos theta. So E dot n cap is E cos theta. E cos theta is, we'll use this in our expression for flux. Let's see. Basic formula for flux is phi is Es cos theta. This is the basic formula. Phi is Es cos theta. Rearrange it in this form. We have rearranged it so that this E cos theta could be replaced by this E dot n cap from our equation 1. So from equation 1 we'll substitute this E cos theta as E dot n cap. So we get this formula for flux. Phi is E dot n cap into S, where n cap is unit vector along the normal to the surface. Many times n cap S, these two together, n cap and S, these are together termed as area vector. This n cap S is S vector or the area vector. So the flux could be written as phi E dot, this whole will be S vector, E dot S vector. This is the basic formula for flux. So now we have the basic expression for flux. Phi is Es cos theta or E dot n cap S or E dot S vector.